Alright, hello everyone and welcome back. So in this video, I'm gonna do more example problems of finding arc length of a curve. Okay, right. So here we have the curve y is equal to natural log secant x going from 0 to pi over 4. So you want to find the arc length between those x values of this curve. Right, so the formula is integrate from a to b square root 1 plus dy dx square dx. Right, so first thing we need to do is we need to find the derivative. So that can be a little bit challenging here. So here we have to use the chain rule because we have a composite function, a function inside another function. So first we differentiate the inside function. So if you differentiate secant x, you're going to get secant x tangent x times, now if you differentiate natural log outside function, we are going to get 1 over secant x. Okay, derivative of natural log x is 1 over x. Right, so the secant x cancels out, so the dy dx here is tangent x. So that's your derivative. So let's plug this information into the formula. So ab, that's 0 to pi over 4 square root 1 plus square of the derivative is tangent square. That's what we get. Now to integrate square root of 1 plus tangent square x, we know 1 plus tangent square from the Pythagorean identity, it's equal to secant square x. So I'm going to replace it from secant square x. So now the square root of secant square x is secant x. Okay, right. And if you integrate secant x, you're going to get natural log secant x plus tangent x, absolute value of secant x plus tangent x. And then you have to evaluate this at pi over 4 and 0 and subtract. So if I substitute pi over 4, it's natural log secant pi over 4 plus tangent pi over 4, absolute value minus natural log secant 0 plus tangent 0. Right, so natural log secant pi over 4, well, secant x is same as 1 over cosine x. And cosine pi over 4, if you remember the unit circle, it's 1 over square root 2. So if cosine pi over 4 is 1 over square root 2, 1 over cosine pi over 4 is the reciprocal of 1 over square root 2. So that's square root 2. Plus tangent pi over 4 is sine pi over 4 over cosine pi over 4. It turns out that sine pi over 4 is also 1 over square root 2 and cosine pi over 4 is also 1 over square root 2. So if you cancel them out, you get 1. Now you don't need absolute value here because square root 2 plus 1 is a positive number. So there's nothing negative to make it positive. Minus natural log secant 0 is, well, secant 0 is same as finding the cosine 0, right? If you know cosine 0, you can find secant 0. Cosine 0 is 1, so secant 0 is also 1. Plus tangent 0 is 0, okay, because sine 0 is 0. So what we have is natural log square root 2 plus 1 minus 1 plus 0 is 1. So again, you don't need absolute value because 1 is a positive number. But natural log 1 is 0. So the arc length here is natural log square root 2 plus 1. Okay, that's the arc length of this curve. So besides from applying substituting stuff for the formula, we needed Pythagorean theorem and then the integral of secant and the unit circle to find the length of this curve. Okay, right. So yeah, I'm gonna do kind of a different example in this video. My second example is kind of a different. So let's check that out. Okay, so here's the second problem. So in this problem, as you can see, I have given the limits of y rather than x. So if you remember our arc length formula, okay, we are integrating with respect to x. So we need the limits of x. Where is x going from? Okay, from where to where? Now, you could find the limits of x by plugging the values of y here. But rather than that, something that we can do and sometimes something that's helpful is to write this formula in terms of y. That means when we are deriving the formula, remember, we said that the horizontal distance between 2 points in a line, in all the lines, that's same. So delta x is same. But instead of doing that, we can make the vertical distance between each line to be same and change the horizontal distance. So if you do that, then our formula going to be written in terms of y. So here instead of dy dx, we are going to have dx dy square dy. Now you integrate with respect to y and the limits belong to y. Sometimes this is easier to use because sometimes if you express the function in terms of y, maybe it's easier to integrate, like in this instance for it. Okay, now so that's what we are going to use in this example. Okay, now to do this, we need to rewrite this function in terms of y. That means we need to make x subject. If y is subject, you can easily take dy dx, differentiate the function with respect to x and find dy dx, okay, because y is the subject. And if everything is written in terms of x, then it's easy to take dy dx. But if you are hoping to get dx dy, that means you need to write the function in the format of x is equal to the terms of an expression or an expression of y. Okay, so you need to make the x subject. So to do that, what I'm going to do is I'm going to cube both sides. So it's y cube. So if you cube x to the 2 over 3, okay, these 3 cancel out. So you're going to get y cube equal to x square. Now you're going to take the square root of both sides. That means the half power. So 2 to the half, 2 cancels out. So x is equal to y to the 3 over 2. Now you have x as the subject in this function. Okay, that's what you need to do if you are thinking about using the formula that's written in terms of y, or if you are integrating with respect to y. Now you can easily take dx dy. Now you can easily differentiate x with respect to y. So y to the 3 over 2, if you differentiate, 3 over 2 comes out, subtract 1 from 3 over 2, right? So dx dy is going to be 3 over 2. If you subtract 1, it's y to the half, right? So that's your derivative. Now you can use the formula that's given here. So let's use that. Now the limits of y, they are going from 1 to 8. Right? Square root 1 plus, now the square of this dx dy. So 3 over 2 y to the half square dy. So 1 to 8 square root 1 plus, if you square it, 3 square is 9, 2 square is 4, y to the half square is y, right? 2 cancels out in the power and you get y. So you just need to integrate this. So integrate this, we can use integration by substitution. You can choose u to be the inside function, what you have inside the square root. So u is 9y over 4. So then du dy is going to be, if you differentiate u with respect to y, you're going to get 9 over 4. Derivative of 1 is 0. Derivative of 9y over 4 is 9 over 4. So dy is du over 9 over 4. That means dy is 4 over 9 du. Right, now you need to change the limits. So if y is 1, u is going to be 1 plus 9 over 4, which is u is 13 over 4. And then if y is equal to 8, u is 1 plus 9 times, here you plug 8, 9 times 8 is 72, so 72 over 4, so that's 18, 18 plus 1 is 19, so u is 19. Now we have a new integral, we are going from 13 over 4 to 19, that's where the u values are going from, so square root of u, dy is 4 over 9 du. So this is same as, we can take 4 over 9 out. So square root of u is u to the half. So you are integrating u to the half from 13 over 4 to 19. So if you integrate u to the half, you're going to get u to the half plus 1 divided by half plus 1 times 4 over 9. Evaluate it at 19 and 13 over 4 and subtract. So this is 4 over 9, u to the half plus 1 is 3 over 2. divide by 3 over 2, and still need to evaluate at 19 and 13 over 4. So here dividing by 3 over 2 is same as multiplying by 2 over 3, so it's 8 over 27. Now let's substitute 19 and 13 over 4. So 19 to the 3 over 2 minus 13 over 4 to the 3 over 2. So yep, so this is the arc length. Okay, I don't think there's a better way to simplify this unless using a calculator. But yeah, that's the length of the curve. But the biggest thing here is that we can actually use the arc length formula where you can integrate it with respect to y, so that you integrate with respect to y rather than integrating with respect to x. But the most important thing is, if you are doing that, the limits should be in limits of the integral should belongs to y. Okay, and then the other thing is that you need to make x subject. If x is not the subject, you have to make x subject, and then you can find dx dy. Okay, right. So in the next video I'm going to solve another example, and yeah, I'll see you in the next video.